RLC theory. So what is RLC? So RLC, the symbol stand for R for resistor, L for inductor, and C for capacitors. So what happens in an AC circuit, as you vary the frequencies, there will be a reactance. And so the inductor and the capacitor reacts in the circuit when it receives a AC signal. So there's two types of RLC circuits. You get a parallel RLC and a series RLC circuit. So we're going to look at a pure resistor. So a pure resistor has no inductance and no capacitance between its ends, only electrical resistance. When a pure inductor is connected to an AC supply, the current which flows at a constant will always be directly proportional to the applied voltage and inversely proportional to the resistance. So here we're looking at a not pure resistor. Okay, so in reality, every resistor will have some sort of capacitance and inductance. So in this case, we're looking at when it's not pure. Don't forget, this is our AC wave, which is a sine wave. So when you see this symbol, it means AC current. So we have XL, which is our reactance of our inductor, and XC, which is our reactance of our capacitor. So notice that X means reactance. So notice that reactance is in opposite directions to each other. So the reactance of the inductor is on top and the reactance of the capacitor is on the lower side. Notice that there is 90 degrees, okay, between XL and R and XC and R. So in effect, they are 180 degrees apart from each other. So 90 and 90 is 180. So this is what we call the phasor diagram. So looking at it again, we can see that if XL is greater than XC, then the phasor, the resultant is going to be, so the resultant phasor is going to be on the top over there, right? Because XL is greater than XC. And this angle is called the phasor angle. So when your phasor angle is 0, this means the power factor is equal to 1. If there is a slight angle here, then the power factor will be very close to 1. So it will be 0.9 or 0.92, 94, 98. If this phasor is very close to the resistance phasor, then as soon as it's exactly the same, the power factor will be 1, and the phasor angle, this angle, will be 0. Remember that rotation is anti-clockwise. So when we have voltage, notice the voltage will start here at 0. So this is our AC signal, right? So that's our voltage starting at 0. That's our AC signal. And the current will be out of phase. So notice there is a slight angle, because remember, here's 0 degrees, here's some angle, so there's a certain angle between there. And so this is the same phasor angle here in the diagram. So notice that they are out of phase. So here we'll say that the voltage is leading the current, or the current is lagging the voltage. Why? Because the current here in black is starting a little angle later than the voltage. So here in the phasor diagram, we can clearly see that the voltage So if voltage is on top here, which is normally voltage is here, and this is the current, so we can see that the voltage is leading the current. Okay, so with inductors, the voltage leads the current, and with capacitors, the voltage lags the current. So where resistance is, that is also the current phasor, and on top, this is the voltage, right? And here at the bottom is also voltage. So we find that in this case, with the XL being greater, we find that the voltage leads the current. Right, we can also say that the current lags the voltage. So once again, the voltage leads the current when XL is greater than XC. Right, so notice if XC was larger, then we'll have a phasor angle in the bottom. We have our voltage, which always starts at 0. Then we have the current. Notice that the current is leading the voltage, means that the voltage is lagging the current. So if I is the current and this is V and at the bottom is also V, this means that the voltage is lagging the current. Okay, and the current leads the voltage. Right, so with capacitors, an easy way to remember it is that the capacitor is the captain, and so the current leads. Okay, so with caps, the current leads. With inductors, the current lags. And so it's good just to write down those two things to remember it. Right, so with RLC circuit, we have a pure resistor. With a pure resistor, what will happen? We will get the voltage, which always starts at 0, and the current, which is in phase with the voltage. Notice here, there is no leading and lagging. So this is what we mean by a pure resistor. With a pure resistor, there is no phase angle because there is no capacitance and no inductance across its ends. So this is what we mean by a pure inductor. The voltage and the current are in phase with each other. Current is in phase with the supplied voltage. Okay, so if we were to draw a phasor diagram, okay, the voltage and the current are in phase. Do note that the I and the V are on exactly the same line. I just drew it like that so you can see the difference between the black and the blue pen, okay? But they're on top of each other perfectly. So they're perfectly in phase. Right, so now we're looking at a pure inductor. So with a pure inductor, there is a back EMF. And this back EMF will be induced across the ends of the conductor, right? So here's our phasor diagram, and the arrow here coming down in black, that's the back EMF. Notice that the back EMF is in the opposite direction of the applied voltage. So they are 180 degrees in the opposite direction. So they are out of phase. So we have Lenz's law, which fulfills this. That's the EMF generated in the coil. Its direction is opposite to the change that produced it. Now we're looking at an AC signal, which will provide a current through a capacitor. So with a pure capacitor, the plates charge when coupled to an AC supply. The potential across the plates will rise and will fall in sync with the supply. So as the AC wave goes up, you'll find that the potential across the plates will rise, and when the AC signal goes down, you'll find that the potential across the plates will fall. Okay, so as it heads in a downslope. Right, so V and Q, notice Q is the charge. So if we have V there, or the voltage always starts at 0, and then we have our Q. So our Q, our charge, will be in phase with the rising and the falling. And then we have the current. The current will lead by 90 degrees with the capacitor. So if we draw the phasor diagram, there we go. We'll have the voltage at the bottom, the current there. So there's a 90 degrees between the voltage and the current. Alright, and so this means it is 90 degrees out of phase. With the inductor, don't forget, the inductor is also 90 degrees out of phase. Okay, so here we have XL. XL means inductive reactance. So we have frequency. So as the frequency increases, what will happen to the XL value? It will also increase. So as that increases, notice that XL is going up and the frequency is going up. So as the frequency increases, XL increases. So the formula for inductive reactance is 2 pi FL. Notice that if F increases, XL increases. If L increases, XL will increase. This is what we call directly proportional. So this graph here is what we call directly proportional. When AC voltage is applied to either a pure inductor or a pure capacitor, there appears to be some sort of resistance. This resistance is called reactance, which is denoted by X. Okay, so when you see X, so X is equal to XL minus XC, or X is equal to XC minus XL. So that's how we normally write it. To say whichever one is bigger, it will go in the front. So here we are saying it is 90 degrees out of phase. Inductors. So with inductors, it is 90 degrees out of phase. And now with capacitors, it is also 90 degrees out of phase. XC means capacitive reactance. So the formula here is XC is equal to 1 over 2 pi FC. If C increases, XC will decrease. If F increases, XC will decrease. XC is inversely proportional to F. So if we were to draw this, the relationship as F increases, what would happen to XC? XC will decrease as seen in the diagram on the right. Okay, so as F increases, XC decreases. This is what we call inversely proportional. So now we have a RLC circuit: resistance, inductor, capacitor. So inductors are normally in henries and capacitors are in farads. So the relationship between XL and XC is 90 degrees apart with the resistance, but 180 degrees apart from each other. So XL is working in one direction and XC is working in the opposite direction. If the frequency changes, starting at a very low frequency, this means XL will continue to rise while XC is coming down. It will get to a point where XL is equal to XC. This means the overall effect of L and C will cancel, and this was when the circuit will be at resonance. So the formula for impedance will be R squared plus the difference of the reactances squared, Pythagoras theorem. So if XL and XC are the same value, this will give us 0. This would mean that Z is equal to R at resonance. Also, I is equal to V over Z to find the current in a series circuit, which is the same at all points of the circuit. So the current in a series circuit is all the same. So if Z is equal to R, and those are our formulas, this means that if Z is bigger, that means XL will not be equal to XC. Now, since Z will be equal to R at resonance, we are now getting a smaller value for R than before, because remember, impedance is a bigger number than reactance normally, but at resonance, this Z will be equal to this R, which means that it went from a big number Z to a smaller number Z. So as a result, what will happen to I? You will find that if the resistance went down, right, so it went from Z to R, and R would be at its lowest points, because why? XL is equal to XC. So if R goes down, I will increase. Okay, so I and R are indirectly proportional. So they're not directly proportional, they are indirectly proportional. What is proportional in the circuit is I and V. So I and V are proportional, but I and R are indirectly proportional. So the current is maximum at resonance. Why? Because XL is equal to XC, which means that Z is equal to R, so I is maximum. Z is therefore minimum, because they are inversely proportional. Power factor is equal to 1, cos theta is also equal to 1. This means that the phase angle is 0. Z is a combination of RLC. So Z is impedance, it's a combination of RLC. It's a complex form of opposition to the flow of current. So remember that resistances resist current, but X is a opposition to the flow of current, and collectively we now have a complex form of opposition to current flow. So here we have I that is flowing in the circuit, right? So above we have the impedance formula, and here we have current flowing in a circuit going through the resistor, the capacitor, and the inductor. So current is the same in all parts of the circuit. So this means IR, so the current that flows through R is called IR. The current that flows through XC is IXC, and the current that flows through L is IXL. You with me? And the current is the same in all parts of the circuit. So V, we can calculate the volt drop across the resistor, and we can calculate the volt drop across the inductor and across the capacitor. So the volt drop there will be I times R, which will give us the volt drop. Across the inductor, I times XL. Across the capacitor, I times XC. Okay, because the current is the same right through the circuit. So once you have the current in an RLC circuit, you can easily now find the volt drops across all those three components. Do note, you cannot add those three voltages up, VR, VL, and VC. You can't add them up and get the supply voltage. Remember, it'll be Pythagoras theorem. So voltage total is equal to IR squared plus IXL minus IXC squared. Obviously, whichever one is larger will come first here. Okay, so this is how we will get the voltage total. Now all those formulas can be swapped out, because IR is VR, right? And IXL is VL, and IXC is VC. So that's our formula for total voltage. So now we have XL minus XC, if XL is larger, and then we have R. So this will be the phasor diagram between these. Dropping a perpendicular, so remember our phasor diagram, the phasor impedance always goes from the center of the Cartesian plane, like in mathematics, and then we drop a perpendicular. So we can calculate this angle using the trig ratios. So cos theta is equal to R over Z using the diagram, And that's what we call power factor. We can also calculate it using these values. So cos theta is equal to VR over VT. To find the angle, it'll be theta equals to cos to the minus 1 R over Z, or cos to the minus 1 VR over VT. And this is how we can calculate power factor. So XL is more than XC. So that is our phasor diagram. When XC is more than XL, this will be our phasor diagram. So notice XL is always on top, XC always at the bottom. For series circuit, that is. Right, so now we get IT is equal to IL, which is equal to IC, which is equal to IZ, which is equal to IR. Why is this the formula for series circuits when it regarding to current? It's because the current is the same right through in a series circuit. Now we're looking at the power triangle. So with the power triangle, we have power reactive, which is the vertical, and power true, which is the horizontal. And then power apparent is our hypotenuse. So the formula here for power factor will be cos theta equals to true power over apparent power. True power's formula is VI cos theta, and apparent power is VI. This makes the formula so true because the left hand side both balance. So now we're looking at the formula for true power. True power is VI cos theta, and the unit there is watts. We call that real power, true power, actual power, all the same thing. So Q is the reactive power, and that's in VAR. And S is the apparent power, which is S is equal to VI, which is VA as the unit. Okay, so the unit for apparent power is VA. Reactive power is VAR, R for reactive. True power is also volts times amps, but we don't write VA, we write watts instead. And the symbols are P, Q, and S. So power true is VI cos theta. Power reactive is VI sin theta. Does that make sense? According to the trig ratios, opposites over hypotenuse, right? So notice that reactive power is VI sin theta. True power is VI cos theta. The formulas to calculate the power. And the apparent power is just VI. So, power factor important in discovering how much useful power there is. Okay, so this is why we need to know what's the power factor. So useful power, we're meaning the power that is actually being used. So true power is actually the power that is transferred to the load. So let's say, for example, if my power factor is not right at my home, I could be paying for 350 kilowatts, but in effect, I'm only using 300 kilowatts. 50 is being lost due to all the motors that are running at my property. So our highest power factor is equal to 1. This means I'm paying for 350 kilowatts and I am using 350 kilowatts. We call this unity power factor. This means there is no power being lost. What is used is what is paid for. So I am getting 100% use of my power. So 1 is equal to 100%. All power paid for is equal to all power used. So let's say, for example, you have 0.9. This means I'm only using 90%. 10% is being lost. Okay? problems, motors, they have very large coils. And so when you switch on the power, they cause a lag, as we've learned in RLC circuits. So when this lag happens, it causes a power factor. It causes the current to lag the applied voltage. Okay, so motors have highly inductive loads. An immediate current lag occurs when we switch on the power. We can correct this by power factor correction. So what is power factor correction? How is this done? This is done by adding capacitors in parallel with the load. This then has a cancelling effect because it will move the lagging current forward and bring the voltage and current in phase. This has a cancelling effect which will reduce that phase angle. Because why? It will move the lagging current forward, thereby saving the business factory money.